Beaton, and I am a chemistry professor here at Adams State, and it's my pleasure to introduce your next speaker. Kailee Potter is going to be talking about a project that she did this last summer at an REU at the University of Maryland. And an REU is a research experience for undergrads. Research One schools will get money to bring in undergraduate students in science from smaller colleges so that they can go and experience research in a big setting with lots of grad students and postdocs and all that. And so she got to do that this last summer. And currently she is a senior chemistry major. She's going to be graduating in May. And she has a job lined up at the National Renewable Energy Lab in Golden, Colorado. And so I will let her introduce her topic.
Thank you all for being here. I'm going to talk to you today about the stability of nickel and copper complexes with desferrioxamine B at seawater ionic strength, and I'll go through what all of that means. Okay, so this is a brief outline. I'll go over what is a sitter-for, talk a little bit about the metals. This is, as most of you may notice, this is kind of like the scientific method, and I'll just apply this to what I did. So first, kind of where was I? So we're the orange star on there, and the state of Maryland is in the bright yellow oval. And then that little, where the arrow points, that's where Solomon's is. It's teeny tiny little town. So that's where I spent my summer doing this project. Okay, so what I'm going to talk about first is sitter-fors. So what is the sitter-for? Sitter-fors are a class of organic ligands. Desferrioxamine B is the sitter-for that I used, but that doesn't tell you too much about what a sitter-for does. And to explain that, I'm going to start with iron 3. So iron 3 is an essential nutrient, and it's present in low concentrations in the ocean. That's partially because it's only partially soluble in water. But these microorganisms need iron, so they need to come up with a way to very efficiently and very effectively take up this iron. And one way they do that is sitter-fors. And how does that work? So the structure on the screen is desferrioxamine B. I'll be referring to it generally as DFOB. The red areas are the functional group that's going to interact with the metal. So this is what the complex looks like. So this tiny little gray one in the middle, that's the metal. So this is iron, and this whole other molecule is DFOB. And so this is what it looks like uncomplex. So really kind of big molecule. So how this works is these microorganisms create this molecule and they cast it out into the ocean. And this DFOB complex is very, very strongly with iron 3. And so when it encounters an iron 3, it'll bind and form that complex, bind really tightly. And then these microorganisms recognize the bound form, take the whole thing back up, extract the iron, and sort of recast the sitter-for to collect more iron. So why DFOB? If it's this whole class, why did we choose DFOB? DFOB is currently the only sitter-for being produced commercially in macroscopic quantities. So the first metal we're going to look at is nickel. We're all familiar with nickel, right? So these are some ocean profiles of nickel. And the way to read these is on the x-axis you have concentration, and on the y-axis you have depth, so you're going down in the ocean. So nickel is in the middle, and the key thing about nickel is that you can see it resembles kind of phosphate in the upper oceans, like above 800 meters. And then it starts to look more like the silicate profile at depth. And why is that important? Why do we care? And the main thing is if it has a similar profile, then maybe it's undergoing similar cycling processes as phosphate in the upper ocean and then silicate at depth.
So why do we care about nickel?
We don't know a whole lot about nickel in general, and it's a really understudied metal in terms of ocean systems, how it interacts and reacts in the ocean. So the next metal I looked at was copper. We're all also very familiar with copper. So this is copper's profile. And as you may notice, it looks nothing like the silicate profile, the phosphate profile, or even the nickel profile. It varies almost linearly with depth, which is something that we don't see in any other metal. So really kind of interesting that it does this. So the importance for copper is that it's an essential nutrient for some bacteria, for some processes, but is also in high concentrations, it can be very toxic. So it's an important metal in an ocean system. So the objectives of my project. I was trying to determine the stability constant for the copper DFOB complex. So does this metal, the siderophore that binds generally with iron, will it form that same kind of complex with copper and with nickel, and how strong is that complex? So why do we care? First of all, science is cool. That's the main reason why we care. But also this can lead to better speciation models. Having this information, we can put it into a database and figure out how do these different molecules play a role in the ocean. And then the other thing is metal remediation. The DFOB is actually used for iron overload disorder. So if it bonds very strongly with other metals, then maybe it can be used for other metals as well, not just iron. So preparations. So to start with, I made up 40 millimolar solutions of both of my metals. To get exact concentrations, we measure them on the ICP-MS. We're used to like 4 sig figs, milligrams or so. And this does stuff in like parts per billion is the range that it detects. So this is really a pretty exact value for these. Also made up stock solution of DFOB, but that had to be made up daily because it decomposes over time. So that had to be made up every time I ran a titration. And then the background solution. We did it in 0.7 molar sodium perchlorate, and 0.7 molar is the same ionic strength as seawater. But, so why perchlorate and not chloride? I'll go over it in a little bit. So any of you who've taken a chemistry class may be able to relate to this graphic with titrations. They can be very, very tedious and very, very frustrating. Fortunately, I got to use this fancy auto titrator. Really, really cool machine. So the initial titration that we did was, I didn't do this titration, this DFOB and sodium hydroxide. This was just to see, so you're titrating up with base, and you're just trying to get a baseline of how does this DFOB react. Because there's all those hydrogens on those groups, and those will be lost as you go to higher and higher pHs. Then we did titrations of the metal. DFOB was kept constant, and then we varied the metal concentration to achieve these ratios. So the specifications for the auto titrator. Tiamo software, it's a potentiometric titration, which means that you're not actually measuring pH, you're measuring a change in the millivolt reading, which gets converted into a pH. It's a little different. So all of this glass vessel down here, right here, this is where your metals go, the DFOB, and made up in this background solution of the perchlorate. And we use perchlorate because the chloride actually does form a complex with our metal, and that would mess up our data if we have complexes with chloride, not just DFOB. So all of it starts in this reaction. This vessel is water jacketed, means there's water circulating around the outside the whole time to keep a constant temperature. We sparge it then too, which means we bubble into it to remove all of the air, and this prevents CO2 in the air from dissolving and forming carbonate. So we titrated with base, sodium hydroxide, from a pH of 3 to a pH of 10 because that's the range where we see our protons being lost. So this is a titration curve. This has been normalized in moles void for moles of DFOB. So the one in black is this here is just the DFOB. And then the one in blue is copper, and the one in red is nickel. The copper and nickel, you can see, behave very, very differently. You might expect them to be similar, but they're not at all. They bind very differently. So the analysis that was done with this Fiticule 4.0. It's a computer modeling program. Might still be in DOS, a very, very old program, but no, it's designed to find these stability constants. So it's an old program, but it still serves its purpose. Okay, so these are my results. So the log beta values on the top, those are the stability constants. That's what tells us how tightly does this bind to our metal. Does this DFOB bind to the metal? Log beta 1 corresponds to one hydroxamate group bonding to the metal. So one of those circled groups bonding to the metal. And so 2 is 2, and then 3 is the fully complexed metal. So the first row is iron, and I put that up there just so you get a perspective on what does this look like? What's our scale? And so at a constant of 30, that's a really strong, this molecule is in some sense designed to pick up iron, so 30 is a really strong complex. Copper, we have, it bonds less strongly, and there's a missing beta 3, which I'll come back to, but it agrees relatively well with other published data. And then for the nickel, we have all 3 beta values, and they also agree relatively closely to this other published data. So this missing beta 3, what happened was when we did the regression, so we ran this to this model, it kind of bounces back and forth between values, and it eventually converges on a single value, and that's your constant. However, our values never converged. We tried up to 120 iterations, 120 back and forth, and we could never get it to decide on a value. So recently we did some literature research, and what this is that copper forms a different sort of complex. So in the case I had, each of those bonds is equally spaced, equal distant. But in the case of copper, the two, like the top and bottom bond, kind of get elongated. And what that means is that hydroxamate group, it would form a 5 ring, but because that bond is elongated, it can't actually fit. And so you only get the 2 hydroxamate groups to bond on the equatorial bonds and not on you don't get that 3rd bond because it's too long. It just doesn't fit. So in some sense, achieved what I was looking for. I did find stability constants, for the most part, for these copper and nickel. Didn't expect to not find the beta 3, but actually, I'm going to go back a second, because if you'll notice the value for the copper for our beta 2, this value here, see how it falls between these two, and they have a beta 3? That's actually because in some sense, they forced the fit. They said there should be 3, and so picked 3, but these really are too close to be able to be considered 2 separate events. So, but ours falls right in between, which makes sense, because they kind of have like a spread of data around this one point. So we did find stability constants. And then back to the ocean profiles that I showed you, Rulin and Qual, they found this class of unknown organic molecules. And it's got a stability constant for copper of 11.5. So our copper, neither one's really close, but it's in the middle, which means it's in the right range. So what can we say about how what we found relates to this study where they found something that complexes with copper at this strength? What that means is these molecules that they found may be siderophores or siderophore-like molecules because it's not DFOB because it's not close enough, but it's in that range. So it's very possible that it's some kind of chelating organic ligand. And then the future work is the speciation modeling. So that's basically taking these constants, plugging them into another computer program, it's essentially a giant matrix, and plugging in all your possible like anions and cations and different complexes that'll form, putting this all into a giant matrix and seeing, based on like stability constants and where are they at different pHs, how do all of these things interact in the ocean. Some acknowledgements. Maryland Sea Grant and the National Science Foundation funded this project. My mentor for the summer was Dr. Johann Schiff. Emily Christensen was the graduate student I worked with, and she really helped me out a lot with this project. I'd like to also thank the ASU Student Scholars Day Committee for providing this opportunity for me to present this information. These are all of my literature references. Are there any questions?